So we're here with Tohru and also with Patrick. They were with us already like a year ago or something like that, and they already presented Xenomorph to us. Now they are coming to do another learn and share session, and this time on their latest work on IVC related stuff, in particular here, proving non-native operations, taking profit of IVC. Uh, as always, thank you very much for agreeing to come here and take some of your time to present all of this work to us. And the floor is yours. So whenever you want, Patrick.
Thank you for the introduction. So this work is with the team at Aztec in general, and also Toru, who worked on it while he was still at Aztec, and also Liam Egan, who has been discussing with us these issues quite a lot. So it is about proving non-native operations in IVC natively and in one go at the end of the computation. And we're going to see what all those words mean throughout the talk. So first, the context of the work is incrementally verifiable computation. So in this context, there is one computation, here is denoted f, that is applied repeatedly throughout time. So you start with some input x0, and then you have like some non-uniform advice, wi in general, and you can continue the computation like this. And this occurs, for instance, when you're trying to build, for people who are in the audience probably familiar with this, like a VM. So you probably have like some fixed instruction set, and throughout your computation, you want to break your computation in small pieces, and you only want to like execute a certain number of CPU cycles at each time, and then this is how you proceed to write your computation through time. And importantly, you want to be able to prove at each step that what you have executed thus far is actually correct. So you want to say, okay, given x0 and some output xi, I want to produce a proof pi I such that proves that basically I knew intermediate witnesses that led from x0 to xi. And importantly, one can then take just xi and the proof that it's correct, and do one more step of the computation without knowing all the intermediate computation output and witnesses. So if you look at one precise step, so you start, there should be an xi here. So you start with xi and you want to do one step of the computation. So I'm just zooming in into step I here. And you also have like your proof pi I, like I just said. And because you also need to know, whenever you're computing proofs, you need to know the starting point of your computation. You also have like a wire for x0. And then you feed all of this into a prover at step I, and then you produce your proof that the next output xi plus 1 is correct. So this is what is happening here. And so to look a bit more at the syntax of IVC, so it's just basically just writing in math what is already depicted on the diagram. So the prover gets like the starting point of the computation and some claim output, and also then gets as advice, xi, pi I, and wi, basically, from which you can compute the proof, the next proof. And really, when Valiant in 2008 introduced IVC, the idea was computation can run for an astronomically long amount of time, and at some point you only need to know the last output and the proof is correct to continue, and it doesn't even need to be the same party that would continue the computation. But now today we have those applications, and for instance, it's also what we would use at Aztec, for instance, to prove that we have correctly executed a function privately. So for those who know a bit about Aztec, we're trying to have like this programmable smart function where you can have like some private state, and you can also prove that new state is results from the computation of the execution of some function that is in some set of allowed functions. So what I just described in this stack proof paper that came out maybe around a month before this one. And given the computation output and the proof, there's a verifier that can check if that is correct or not. So I've just given the context so far, and now we need to see, okay, what is exactly the problem? But I cannot explain what the problem is that we're trying to solve before I show you how these IVC schemes are usually built. And I forgot to mention at the beginning, if there's any question, please feel free to ask throughout the talk. So a first construction of IVC is from universal snark. So you basically have a snark where, you can pick whichever circuit that you like, and you can prove the satisfiability of that circuit using that snark. And there's a very neat and simple idea to build IVC from it, is to say, you know, I the prover knows Xi, so and Wi. So the prover just says, well, if I start from Xi and I have advice Wi, then I do result in Xi plus 1. And I also simply prove that the IVC prover for the previous step would accept the previous proof. That I know, which is a secret. So Xi, Wi, and pi I are private inputs. And yeah, my claim is just I've done one IVC step correctly, and I proved that the previous output would have been accepted by the IVC verifier of the previous step. And I do this using the universal snark. So the circuit to which I'm applying this snark is, that it depends on the step which you are. And that's a very simple idea, and that works, except that it's not super efficient in practice. And one reason is that if you look at the efficient snarks today, like, I don't know, if you think of Plonk, hyper-Plonk, all these, they somehow eventually run like a KZG verifier, or you can even use transparent schemes and everything. So at some point, you end up having to deal with some multi-scalar multiplications and especially some pairings. So, and then constraining those pairings is very expensive. So later, there was another idea that came out. So there are ways which we're going to talk about to sort of mitigate this issue when it comes to multi-scale multiplications, but pairing is a bit more annoying. But to avoid pairings altogether, you can think of using folding schemes. And what are folding schemes? So let's say you start with some NP relation, so meaning that you have some relation that sort of captures all efficient computation that you may want to do in practice. And you want to, like, for instance, let's say the satisfiability of a circuit, of a arithmetic circuit. And you want to basically divide a two-party scheme where you have some prover and some verifier, and they interact. And the goal is to reduce the proving the satisfiability of two instances to just one. So at the end of the interaction, the verifier just gets like just only one instance, and the prover has a witness for this one instance, if indeed the first two witnesses for each of the circuits that is given, of each of the instances that is given, are indeed valid. So essentially, folding scheme is just a way to reduce, checking that one instance into some relation, that two instances are in some relation to just one. And this only makes sense if the time to check one instance plus the time of the verifier is smaller than the time it takes to check two instances. Otherwise, isn't really useful. So, but using these folding schemes now, one can build IVC as well. And the idea is, like, originates, I think, yeah, there's this paper proof carrying data without succinct arguments. And there's also the Nova paper, and there's somehow the same idea around there. So you start with a folding scheme, the FS here. And I should probably say here that the folding schemes that are usually devised are interactive, but you use Vietnamese to make them non-interactive. To be able then to use them into some IVC constructions. This has some implications as to what is actually the security of the IVC we get, because we're using the random oracle that will eventually instantiate in circuit, but let's ignore that for now. So we start with some folding scheme, FS, and there are going to be two instances for some relation. And there's an instance capital UI, which is an accumulator, and it basically attests to the correct computations of all the steps before the previous one. So you had step I, and in U capital UI attests to the correct computation of all the steps before I minus one. And lowercase ui attests to the correct computation at step, sorry, here it's written I should be I minus one. And they have your corresponding witnesses. Those are actually going to be part of the proof. The witnesses are going to be part of the proof pi I that the prover gets as a witness. Sorry, as advice. And from it, what one is going to do is to fold the two, so basically checking the satisfiability of UI capital and lowercase to just one instance, capital UI, and this is where folding seems not useful. And also, there's also one is also going to run the prover to get a witness for this. And now there's a main circuit, and what this main circuit is doing is basically checking one step of the IVC computation. It is checking that this new capital UI plus one is indeed the folding of both UIs. So basically, we went from attesting the correct computation from step 0 to step I minus 1 to step 0 to step I. And one subtlety is also that we need to make sure that the output of the first I minus of the first of step 0 to I minus 2, that output was what was fed to step I minus 1 to chain the computation basically. And this is what you check in that circuit. And this is what Nova calls the augmented function. So you basically check that you check all this, and the instances are actually instances of that circuit itself. So that circuit is checking, one step of the IVC, and then the instance is getting attest to prior invocations of that circuit itself. This may seem circular, but it's actually not, because the way Nova is written, you can define that augmented function just in terms of like the sets in which the UIs and UIs live, belong to, and it's only afterwards that you interpret those UIs as attesting to the correct computation of the I minus one. And then at the end, you have your circuit, and you basically generate an instance for the circuit at step I, and you have witness WI to prove that you have correctly executed the circuit once. And WI and the capital UI plus one makes sure that the output at step I is what was fed afterwards. So this is how the Nova construction works for IVC. And but now it backs to, so now there was something slightly different than what we saw before with snarks, is that you weren't directly dealing with a proof, because the 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 proof here, it consists of two. I'm sorry, it should be a capital. I'm sorry, no, that's correct. So the proof here is a pair of instance witness pairs, one instance for the I step and one instance for all the steps before, and witnesses that all these things are correct. But what this circuit here was getting was the circuit was not dealing with the witnesses, which is basically folding the instances. So this circuit did not consume the entire proof in a sense. Whereas before, what we saw with snarks, the snark was the prover was proving that the verifier of the previous step would accept the previous proof. So it's sort of more or less the same idea, but not exactly. And the question is then, what do these constructions have in common? And I don't mean just the two that I presented now. I also mean, the construction of stack proofs, or these things that are related to memory checking, these techniques. Basically, the goal being, I want to have a framework into which I can cast all the incremental constructions that we have, which is simple, and from which I'm then going to do what we're going to talk about is called. So I first want to understand, okay, what is the common denominator between these constructions? So that's what like the first section of the like past the preliminary, the first section of the paper, past the preliminaries is trying to do. And basically, um, what all those constructions have in common is that they all define some like core function or circuit for the I step. And this function has basically two types of inputs. So there's the public input, which is xi plus 1 and x0. And there is the output at the previous step. And then there's the witness to go from the previous step to the next output. And there is some string, rho, that comes from the proof. It's computed from the proof, but it's not necessarily the proof itself. And so, for instance, in the case of we're going to see what rho is, for instance, and the rationale is that if xi with x0, xi plus 1 with x0 are in this language, then you know, so the constructions guarantee that you have done one step of the IVC correctly, and it's also very likely that the verifier, the previous step, would accept. So this is what they have in common. So for instance, in the case of recursive snark bootstrapping, you know, FI is just basically, well, it's not exactly VI. It's FI, there's a slight mistake here. FI is checking one step of the correct computation and then checking that VI of the verified previous step would accept the proof. And rho is just the proof itself. But as we saw in the case of foldings, it was slightly different. You know, rho I was just basically the instances. You weren't dealing directly with the witnesses, but you also use the check, like the proof that you had correctly folded these things together in the.
Sorry, a quick question.
Sure.
So this is similar to split accumulation, right?
So an accumulate. So in my understanding, perhaps it's incorrect, but you have that accumulation is similar to folding. Is that correct? Is similar. I mean, it's the same and it's the same.
Yeah, I mean, split accumulation is similar to folding.
Yeah,
There
exactly.
was first
Like,
there was
but
notion of atomic accumulation, which is like something like Halo 2.
yeah,
Yeah, okay.
but here I'm talking about the construction of the IVC after you already have your folding slash accumulation.
Okay.
So you have your accumulator or you have your folding scheme, and from it you construct an IVC, right? So it's not you're building one primitive from the other. Is that okay, or does that answer your question, Dev?
No, but let's continue.
Okay, we'll come back to it. So here we have so basically I just exhibited the framework, like not a framework, but basically, yeah, a framework in which the constructions like of IVC fall into. And then, like I mentioned before, stack proofs also fall into this sort of idea and memory checking. So basically, if we start from this framework, we can then, have a technique that it applies to the constructions that we know, incremental, all the incremental constructions that we know that then eventually fall into this framework. So what is the problem that we're trying to solve? So the issue is that Snark and folding verifiers, they usually perform, at least group operations plus other things. And usually you have like a, let's say a group that's going to be like a group of the points of an elliptic curve defined over some field FQ. And in this case, can be like, you can think of BN254, something. And then this group has like some prime order, like the R. And you then have a scalar field, FR, for B and Q, which are, uh, sorry, you then have like a scalar field, FR, which is also prime. And in the case of BN254, you have like a Q which is in between R and 2R. Okay. And since we always then Fi constrains the correct execution of a snark or folding verifier to be correct, that it means that you're writing a circuit over Fr, which needs to simulate operations in FQ. Because whenever you're going to add 2 points or double points, you're going to do those operations over FQ, but you're working over FR. So this is what is called non-native operations. So this is what we're trying to solve, basically. And there exist solutions already which leverage what is called curve cycles. So essentially, you're going to work with elliptic curves such that, if I start with my field, with my group that it's called GQ, that was a subset of the points of an elliptic curve defined over FQ. Then I want to know that. So then I demand that there is, I require that there is an elliptic curve that is defined over Fr now, for which I have another subgroup, which is of order Q. The issue with this is that in the IVC constructions, you eventually need to basically all the operations that you don't want to do, all the non-AV operations that you don't want to do, you have to put them in the other curve, which means you need to have two folding instance pairs. So remember before we had like already two instant witness pairs of folding, one for all the computations up to the previous step and then one for the current step. And now you need to have it twice because you need one per curve because you want to delegate all the operations from which are non-native to your native curves, basically. So, which means that eventually you have like two circuits to prove at the complete end of the computation. There's a paper called CycleFold that tries to minimize the size of the second curve. That tries to minimize the size of this second circuit. So of the circuits on the second curve. So it sort of should already, make the situation already better, but we want to avoid this completely. So, sorry. Yeah. So this then brings us to Goblet and Plonk, what's in this work, and just going to try to explain first the idea, and then we're going to see together how the scheme is built. So you start with, the framework that I exhibited here. So you're saying, okay, there is some function fi that I want to check, and this is how my IVC construction works. And what you do is you basically decompose fi into two series of operations. So some cheap part, like mainly only field operations, I'm going to call F0, and some more expensive parts where you have like all the group operations that you have to prove. And the main idea is to say, well, all the expensive operations, I'm not going to do them. I'm only going to record the input outputs in a table and only prove the inexpensive part. And at the end, I'm going to somehow shift all those operations that I didn't want to prove. That I didn't want to prove. Sorry, there's a typo here. It should be prove native in FQ. I'm going to shift all the operations that I didn't prove so far to the native field, and I'm going to prove it there. The question is, how am I going to shift all those operations at the end? This is what we're going to see. And the main challenge is really to prove that throughout the computation, your record of operations was consistent. That basically you didn't throw away some computations that you were supposed to do and prove at the end, and get away with it as a cheating prover. And you want to prove this consistency, but without having to do then expensive operations again while proving this. So that's really the main challenge. That's what really make things really complicated eventually, but there is a work. It eventually it works. And this only makes sense if, the cost of proving consistency plus the cost at the end for proving that those non-native operations are correct are strictly smaller than the cost of, just doing IVC, but without any of these ideas like proving things non-natively. So this is what we would ideally like to get. And the issue now is that, I mean, not an issue, like from a theoretical standpoint, at each step I said, you're only going to prove the cheap part and you're only going to, record the input output of the expensive part. And you're going to continue the operation as if you never, sorry, you're going to continue the operation using the output that you claim to be correct, but you never proved it. So it means that now that when I give you an IVC proof, pi I plus 1, you are not completely guaranteed that xi plus 1 is correct. You're guaranteed that xi plus 1 is correct only if the proof is correct, but also the information that is in the record is also correct, that the operations that are in the record are also correct. So a way to model this is to say, well, throughout the computation, the proof is going to maintain like some state, which is basically containing the record of operations that were not the record of operations thus far in the computation that were not proved yet. And the verify is only going to be given like a short representation of this record. So like auxiliary input, there's going to be a commitment to that. And like I said, eventually, outside of the scheme, there needs to be an extra mechanism to make sure that these operations that were recorded and for which the verifier is given a commitment that they are correct. So IVC really requires normally that the the proof assures that the proof pi I plus 1 assures that xi plus 1 is correct. So this is not really an IVC scheme anymore because this is not true. There's an extra condition, and this extra condition is not checked by the algorithms of the scheme. It's going to be something that we're going to see later that comes on top of it, but it's not part of the scheme. So one needs to give a precise meaning to what this means. So this is what is introduced in the paper and called like IVC with auxiliary proof information. So where you have, your proofs, but you also guarantee only correct extraction. You guarantee correct extraction only if the auxiliary input is valid. And by valid, I mean that the opening to that commitment is a valid set of operations. So this is the
sorry, another quick question, but this is already a situation with folding that you don't have a proof of like when you have your set of commitment, your extraction is not guaranteed. It only happens if the final decider accepts it, right? So this is kind of similar.
So this is what I was trying to say before. We are going to use a folding scheme to build this scheme. It's like you have your folding scheme that is just one building block from which you are going to build the IVC with auxiliary proof information.
No, I'm just confused. Why is it not IVC? Because like folding is a particular kind of IVC, and it has exactly the same problem. Like, I'm sorry, maybe it's just pedantic, but in folding, your proof also does not attest that your commitments actually correspond to solutions of the circuit or correct execution, right? They only correspond if they like if the final decider accepts them. So in the similar way, you could say that, and also your transcript is correct. So your decider for transcript is like saying that it's correct. Consists of correct non-native operations or whatever. So I'm just confused why are you not accepting this as an IVC? Although technically your transcript is probably limited from above in size, but otherwise I don't see why it would not be like an IVC.
Okay, so if we go back to the definition of folding here that I used, I mean, of course, remove the parameters and key generation that's in Nova. Here, if you look at your folding scheme, you know, there's no concept of I've executed this amount of steps. There's just I have two instances and I reduce to one. There is no notion of having a computation that you're repeating. You're just this is just a building block that you're then using to build an IVC. So folding scheme is not an IVC by definition.
Well, I could say that my relaxed instance has a transcript of deferred operations, and like I mean, it looks very similar to like normal definition of folding. In the sense that I could probably define relations that would satisfy this up to the fact that your transcript is of limited size. But otherwise, okay, whatever.
No, so sorry. Well, we can defer that to the end, but let's perhaps let's defer this discussion towards the end. What I'm just trying to say is that by definition, an IVC, well, a folding scheme and an IVC are two different things, and you use the folding scheme to build an IVC. And what I'm trying to introduce now is an IVC, regardless of however you want to build it, whether it's with folding schemes or not. You could use actually even snarks again. You can bootstrap snarks again. There, I want to build an IVC where I just have this relaxation on the noise silence requirement where I don't necessarily want to extract intermediate witnesses. So I think let's perhaps discuss this afterwards, but I think that there is a confusion between, you know, how I'm going to use folding to build my IVC and actually what an IVC standalone is, regardless of how you want to build it. But yeah, we can finish the conversation afterwards. So wait, so where was I? So here, yes. So compared to the picture that we had before with the IVC, where we just had the proofs and the outputs. Now I'm just adding two things. I'm adding the auxiliary input, the auxiliary proof information, and also the state to the syntax, basically. And now the question is, how are we going to build it? So the starting point is to say, assume that you had an IVC, that fell in, or an incremental construction that fell into the framework that I gave before, regardless of whether regardless of how the the IVC was built. Even though, to be fair, what I'm going to show now is not black box completely, because you sort of need to assume certain things about how things work, but you're not going to. But basically, this is like satisfy all known constructions. So, I gave the main idea here. What I was saying, where I was saying, you record all the operations, you only prove the cheap part, and you prove the consistency of the record without introducing expensive operations. So here we can start. So we start again with an idea. So what I'm going to define, like a function, like a core function, GI, the same way before we had FI. And what's going to get is like the public part. So xi plus 1 and the auxiliary proof information at that point. And what is going to get as also private, like as advice, is going to be the previous output, the string that is computed from the previous proof, and the auxiliary information that came from that proof, and a witness that xi plus 1 is really comes from xi. And what is also going to get are the expensive operations, the record of expensive operations at the current step. Because remember, I said you only, you want to record those operations and prove consistency later. But basically, I want to define such a core function. And one thing I definitely do not want is that it takes the whole accumulated operations throughout the entire computation. Otherwise, then the cost proving this is going to be proportional to that whole accumulator. So it's going to be proportional to the length of your IVC, and this I don't want. And the first thing we're going to do is just make sure that the output of the cheap part is recorded in the operations at the current step. Now let's see how we're going to do the rest that I mentioned. And first we need to say, well, these operations, I'm going to focus then in the case of where we have like elliptic curve operations that we have to prove. So in F1, how do they look like? How can I write them? How can I like express them in a way that I can then check them later and which is amenable to, proving, correct accumulation throughout time. And for this, I'm going to define what you call this elliptic curve state machine. So it's basically just like an abstraction of sequential operations, elliptic curve operations. And in this state machine, what is the state? Basically, I have the second component is a bit. It's just a bit telling you in the past has there already occurred uh, a computation that was incorrect. And the part that is really useful is the first part, which is a state. And from this state is like you start from some group operation. You start from some group element. And this is basically most of what is the state in your machine. And you also have like the neutral element of your elliptic curve, but you also have like two special states, which are like zero, which is like initialization, and infinite, which is like I turn off my machine, basically. And the operations that you're allowed to do is to say, when I start from a group element, I can add another element p, and then my new state is just g plus p. Other thing that I can do, I can, say to the current element, like to the current element I'm at right now, which is g, I want to add 8p, basically. And you can imagine that, if you do like this operation much like add AP many times is the same thing as just saying I'm doing a multi-scalar multiplication. And then at some point, uh, you want to check if you want to check if your computation so far is correct. So you're going to say where I am, is it equal to this claim output? So if the claim output is in the G where you are, you go back to the start of the machine and then you can do some different computation, some different series of elliptic curve operation, by saying, okay, I start to zero. I go back to zero is my accumulator, like the neutral element of the group. Or I can say, okay, I'm done with my computation and I finish and then just put the infinite input and then the machine is turned off. But there's also the case where, your computation was incorrect, or like your claim output, you say, you ask, is where I am equal to some p, which is not g, and then you go back to the start of the initialization step state, but now you have a bit one, which says there was some computation that was incorrect so far. And you can, in the row below, you can do the exact same thing as above, basically. So this is basically just a machine that says this is how you're sequentially, this is how like you're going through your computation of this is how you're going through your elliptic curve computations, basically. And the way you would,
Quick,
yes.
quick question. Sorry. Maybe I missed it or misunderstood. But you don't support negating a point or?
It's the same thing. You can say times
Okay,
minus.
okay, okay. Never mind then.
Yeah, but that's great. The reason why you're doing like times AP is really to support MSMs because the idea is to say you want to do it repeatedly.
Makes sense. Thank you.
And this is just an abstraction. And then how do you actually instantiate this abstraction? Is that, let's say, the example I'm taking now is what is aspect is the Plonk arithmetisation, where you have like an execution trace, which is simply just a matrix with a certain number of columns, and the row is your execution trace size is basically the size of the circuit. And in the Plonk arithmetisation, one applies, constraints to consecutive rows, like one or two consecutive, like two consecutive rows or just one row, basically to write a computation. So this is how the execution trace looks like at two consecutive rows. Basically, I just zoomed in there. So why did I pick four? So you can pick whichever number you want, but the larger the number of columns, um, the more the communication size grows. And four basically allows you to do, for instance, just arithmetic gates where you're saying, I have my left input, my right input, and my output. And I also have like an extra column where I'm going to put basically the permutation polynomial. That permutation polynomial's role is to simply guarantee the correct wiring of the circuit. Basically saying that, the output at gate 5 is indeed the left input at gate 10, for instance. So I just focus on column of size of the table of size with four columns. And yeah, what I'm going to do. Remember that in the case where we're working over a circuit defined FR, and we may want to do some operations with group elements which are in FQ. So each element in FQ, sorry, a point in your elliptic curve is going to be a pair of points x, y with x and y each in FQ. So I can break x in two parts, x0 and x1, and similarly for y. And also the scalar by which I may want to multiply this point, I just recorded here. And remember, the scalar is in FR, so I don't need to break it into. And the operation here, I can just say is just some arbitrary fixed element in FR. It can be 0, 1, 2, 3, 4. They just represent if you're doing, an addition, like so. So that's how you can basically, at each step say, this is the input to my machine, and this is basically basically this is all the inputs to my machine, starting from the state where we are. And you don't need to write down, the bit uh, indicating whether all the operations are correct so far, because all your operations are correct so far only if, basically when you apply your constraints to the entire matrix, your constraints, you always end up with zero, up to negligible probability. So thank you for this. So this basically just gives a structure to the record. This is how the record is going to look. I see there is a question in the chat. Oh, okay.
It's some yeah, I
Let's
think so. We can ignore, I think.
um, so basically now that we have this record, we want to prove consistency, right? So during your computation, the proof is going to hold the matrix, and the matrix of the computation up to the private of the operations, expensive operations up to previous steps, I'm going to call it A1. The operations at the current step, I'm going to call them A2. And the concatenation of the two, I'm going to call them A0. And basically what what is going to be contained in the auxiliary proof information that the verifier will be given are the commitments to the three. And how can one basically prove that, A0 is really the concatenation of A1 and A2? Think of A1, the proof is going to work column by column. So you can really think of just A0, A1, A2 as just being one column. And if you look at basically the polynomials, if you look at in the monomial basis, you look at the polynomials that they represent in the monomial basis, it's really the correct concatenation if this polynomial equation is true. The thing is, you need to know what the length of A1 is, but remember A1 is the whole accumulator of all the operations thus far, and you don't want to give A1 as input because then your circuit is going to be very large to prove. So one way to do this is to say, well, I'm just going to declare a length for A1, and I'm going to let the circuit throughout the computation check that I always add the correct amount at each step. We're going to see that afterwards. But basically now assume that you have an L that is declared, and it's not necessarily true, but for now we assume that L is really the length of A1. So you want to prove this equation here when you're given this commitments, and So you say, okay, I know A0, A1, A2, the coefficients of the polynomial. Just that, if the verifier first picks an x randomly, then, this polynomial here, when I evaluate at x, it is 0. As simple as that. And you can use KZG for this, for instance, to prove.
Sorry, Patrick. One quick question. I got a bit lost in here because like the main thing that we said so far is we are splitting the operations, and field operations go to some place and elliptic curve operations go to another one because we don't want to execute it in the main circuit. So what I'm failing to follow is those two things are usually like interleaved and like entangled, let's say, on a main circuit, or follow some main logic, which is not I have all this set of operations and all this other set of operations. Like they might have connections between them, meaning copy constraints or stuff like that. That you want to be sure that I don't know some coordinate is this, or I don't know, whatever. You want to hash to point, I don't know, whatever kind of stuff it is. So in here yeah, I mean, at least to me, it doesn't look like you are accounting for any of these like original order maintaining or whatever you want to call it. So, I mean, am I just having the wrong intuition, or like how can we?
I'm going to try to answer your question. I'm not sure I completely understood it correctly. So if at some point I'm going to
Hmm.
answer.
Sure.
So what I'm trying to say here is that I'm looking at, the record of operations of all the previous steps, the record of operation at this step, and I want to prove consistency. So the part about splitting the computation between F0, between ECC operations and group operations is somehow already done. It's basically in A2. So at a current step, in A2, what I write is the input and output of the ECC operations. I don't do the ECC operations. I just write, this is the input, this is the operation I was supposed to do, this is the output. And this is what I write in those tables A2 at each step. And when I pack them all together, this is what gives A0. Um, to going back to, you need to, like, what's the relation to the output of the field operations? This is why I was saying that in your main circuit, you're going to pretend that the the clean output is correct. You're not going to check it, but you're just going to consume it. You're not going to check in circuit that these outputs are correct. You're just going to, list. You're just going to make sure that the list is okay, that the list of operations is okay. But each time you just take the output and you pretend you continue as if it was correct because you
Yes.
always check
So,
afterwards.
like, what you mean is you are proving correct accumulation, or correct, like, yeah, correct accumulation essentially of your statement. So on that I agree. But I guess the question is, uh, we are not allowed to have absolutely any extra logic that it's not simply I have a set of elliptic curve operations and a set of field operations, and I want to prove them correctness. You cannot add any extra logic to that. So like they are treated as completely independent operations, and you cannot add extra logic that I don't know allows you to do assumptions between them, or I don't know, like the output of this one is the input of this other one, like having some kind of permutation argument, or whatever it is. You are just proving correctness of computations. That's all.
So,
I think you can defer anything in the same way.
sorry, I didn't understand that. What you said. Could you please repeat?
Yeah, I think you can defer any operation in the similar way. Just you can have more opcodes, for example. You can also defer hashes or whatever you like.
Yeah, that is true, but I'm not sure if that is true, by the way, but I'm not sure if that's what he meant.
I mean, it kind of answers in the sense you are like the main goal here is we are building some kind of call it VM or call it whatever, that its only task is I check correct accumulation of elliptic curve operations, and then I allow you to verify all of those extremely cheaply. Uh, and like that's the task of this, of like the construction. The task of the construction is not like in the Nova case or some of the other IVC/folding schemes where the computation that you are proving is essentially like whatever you want to be. Like this has a very concrete and specific application only in non-native arithmetic proving, let's say.
To be honest, I'm not entirely sure at what you're touching. So in the sense that all the operations that you, so basically all the extra logic that you want to apply to the output of these expensive operations, you can do them in circuit. It's just that you don't want to do in circuit those expensive operations. And in this case, I just looked at ECC operations, but like Lev said, you could put any other operations that you wanted there. But the extra logic, as long as it's cheap, you can put it there. And
Yeah, mhm.
and even like I chose to put ECC operations outside, but I could arbitrarily say I only want to do half of the ECC operations outside and the other half inside, which would make sense. So obviously you want to defer anything, but what I'm saying is that you can really play around with what you decide to put in those records.
Yeah,
Okay, I
I,
see.
I want to
Yeah.
expand. I want to expand maybe on this a bit. You can actually have arbitrary set of precompiles that you accumulate in this transcript, and then you have some custom way of checking them more efficiently. That's only thing that you need for this to make sense. So if you have some customized system which allows you to check some particular kind of precompile, I don't know, deferred operation, let's call it precompile, then this thing makes sense. Moreover, I think in some VMs, people are actually doing precompiles in similar way. So, uh, so indeed, it's very general way of deferring operations.
Uh, I'll just let's just continue. I don't want to take over more time from this,
Mhm.
Patrick, but maybe I can get back at you at the end if I'm
Yeah,
not
and
clear.
I have another question. So I'm confused. Why is it so like, as far as I understand, when you are doing this concatenation, you are making some kind of randomized check in a
Hmm.
point, right?
Hmm.
So my question is, okay, so in each step of IVC, I presumably know the size of my transcript, right? And it's constant sized.
You have, let's say you have an upper bound. Yeah.
So what just prevents me from shifting already existing transcript left and sort of just adding a new one?
Okay.
I mean,
I see your point. You could just say I pick L. Well, I know what L is going to be, so I just use that value.
yeah, I mean, L is program counter multiplied by amount of iterations that you need to do in a single circuit.
Yeah.
So it's
So
it's pretty clear what it will be.
yeah, well, yes and no. So there's this case, for instance, where, for instance, in the case of stack proofs, where you have like some predetermined amount of functions that you want to execute at each step. They do not necessarily all entail the same number of operations.
Well,
And
okay, I can make an accumulator and compute it directly.
this is what's going to come afterwards. So
Oh,
basically,
okay, but I see, I see.
so
So,
basically, isolated the proof system where I said you have some L that you hope is gonna be the correct value, and then in circuit in the logic we are gonna make sure we're gonna have that accumulator, like you said.
so the point is that because L is dynamic, you need this. L is not determined by the circuit itself, and this somehow dynamic and depends on previous steps. You are forced to do this randomized check instead of just static shift.
Yeah. And
Okay.
and also, by the way, remember that I'm doing this check, like the verifier is only doing which the circuit is going to run. The verifier is only given the commitments. So the verifier, I mean, there is no way of checking A0 is really concatenation of the two and doing a static shift. if you don't have them in clear text, or at least
No,
if
no,
you
no, I can. I definitely can. If L is static, I can make okay,
without having
whatever. But
without having A1. Remember, I don't want to give A1 to the circuit. Is that okay?
I think I have shifted A1 beforehand. Okay, no, it's not okay. I agree. I agree. Okay, you're correct. If you do not give me A1, it's the same problem. Yes.
I only want to give like a commitment to it, but yeah. So, like I said before, so this thing is only useful if you know indeed that L is the correct length. And by the way, since I'm using KGG to verify this, there are going to be pairings, but I'm just going to ignore them in the talk because it's just adds an extra complication, which is in spirit not very different from what we're going to do from the rest. So let's look at what the auxiliary proof information that we talked about is going to look like. So you're going to have, your commitment to the record of expensive or input outputs of expensive operations at all the previous steps. You're going to have a declared length, and you're going to have A2, the record of input outputs of expensive operation at the current step. And then A0 is going to be the concatenation of the two, and then you have a commitment to that. And I'm also going to compute, like I showed before, a proof that A0 is the concatenation of the two, assuming that that L is the correct length. Okay, so this is going to be in the auxiliary proof information, which is public. So now, given that, what does the core function do? So remember, we already had we constrained the output of the cheap part to be recorded in the table of operations at the current step, so in A2. And now I'm going to check that, the A0, which was the new accumulator at the previous step, is what is the old accumulator at the current step. So basically, A0 that was in oxi, I want to check that it's the A1 in oxi plus 1. That basically I didn't change between the two. So that's an easy check. Then I'm also going to check that the length L, that is in oxi plus 1, is the sum of the length that was in oxi plus the size of the operations at the previous step. So which means that to G, I need to give the operations at 2 consecutive steps, precisely to check that I've correctly updated the length. So G is only going to depend on the size of operations at only 2 consecutive steps, basically. And by checking this is the accumulator idea that Lev mentioned before, I can always guarantee that the length is correct. This is really how I guarantee that the concatenation proof that I'm going to also consume is also useful and guarantees correct concatenation. And in G, what I'm going to do is I'm going to, check the inexpensive part, because remember the verifier, we again have a KZG thing where, you have some field operations, some group operations, and even some pairings, but I'm ignoring the pairings. And I just want to run the inexpensive part of the verifier. Basically, the proof that is going to be in oxi, because it needed to be checked somewhere. I needed to check. So basically, I take the proof of concatenation at the previous step, and I check it at this step. And I want to make sure that the input output of the expensive part of the verifier is also recorded, because then I'm going to check that at the next step. And that's basically the main logic of the circuit. Of course, I've ignored things here like I've ignored the pairings, like I said. There's also the question of how do you generate this challenge X, because here it's in a circuit, so it needs to be it needs to be deterministic how you derive it. These questions I'm just sweeping out under the carpet because it's just technicalities that obstruct what's the main logic of the circuit. And I'm maybe going to do a pause now to see if there are some questions.
I have questions, but about the decider. So willing to wait if there's more to come on that side, such that it makes sense to ask it.
Yeah, yeah. So right now, I just basically guaranteed that, I correctly recorded all the operations, but we're going to see how we check the things at the end. And one important thing here is that, yeah, the proof size and verification time, they're only proportional to, the size of the operation record at the current and the previous step, not the whole accumulator. Right. The other thing is that the verifier only gets a short commitment to those records. Like, they doesn't get like a full record or anything. And the prover time increases with the record size because the prover needs to compute the concatenation proof. If you're doing a KGG proof, then you have to compute this quotient polynomial. But the size of the circuit, because we're only proving the inexpensive operations, we're not proving the expensive operations. The size of the circuit is also much smaller, so this compensates. So now, okay, I'm going to see, I have my record of operations. I said, I want to prove them natively in FQ. Remember so now I'm going to show you how you can go from a record of operations from FR, you can put them to FQ, and then you're going to see how they prove them natively at the end. So we need to make sure that this translation is done correctly. And you start with, we have R is smaller than Q and 2R, and this was the look of this operation here. So you had a matrix AR, which was basically your record of operations. So basically this is going to be your A0 final at the end, whatever the end is you decide it is. And what I'm just going to do is I'm going to write in FQ now. I'm basically just going to recompute x0 and x1 and basically reconstruct x and y. And a was a scalar in fr, but r is smaller than q, so I could just embed it in fq, interpret it as an element of fq. And you see that by doing this, I just basically half the size of the record. So I had a commitment to AR. I'm also going to commit to AQ. Basically. And now and I want to prove that this was done correctly, that this reconstruction of AQ from AR was done correctly. So for instance, I want to prove that, the up here is really the same as here. How do I do that? So if you look at the entire matrix and you look at all the rows together, you can interpret, all the elements in the first row as some coefficients of some polynomial, in FQ. So it's the same thing as saying that you want to prove this, basically. So one thing so if you want to prove just this, there's also the other thing that you could say, I want to prove that x is really the sum of x0 and x1 at all steps. The reconstruction of x0 and x1 at all steps. But if you understand for the first one, you understand for the rest. So from here, you are given a commitment to AQ and AR as well. And what you're going to do is you're going to evaluate this first column at some random point, x. And now you're going to, in FR, prove the correct execution of an algorithm which computes this sum mod q, because you're doing this mod q, and compare, the output of that algorithm to the claim Vx. And the killing part here, and this is where you have to eventually pay because, you're trying to go from non-native to native. So this is where you're paying because you're proving the correct execution of an algorithm that is doing these operations mod q. And let's see how you can write such an algorithm. So you can basically you can just do a polynomial evaluation algorithm where you start with the first element and then it's basically Horner's, except that you're not skipping one step every time between the indices because the other table was half the size. And you basically just multiply what you had. So yes, it should be W here, WX. So you multiply whatever you have here by X, and then you update your record. And you're doing this multiplication mod Q. And at the end, you check if the output of this in FR is really the claim output that you had in FQ.
Wait, you're actually doing this?
Sorry, what do you mean?
So this is like the actual algorithm that you use?
So basically, I'm just saying that you can use whatever algorithm that you want, and this is
No,
why
I mean, but this is not efficient at all. There are far more efficient methods of computing this.
of compute. I completely agree. I'm just giving just one example of
Okay, okay.
I'm just taking. I'm just saying I want to evaluate that polynomial, and you know, I just want to evaluate that polynomial, and I'm just like compute the output with the other output that I had. It's just that this is a very simple example where you then have, the multiplications mod q that appears, and the mod q, you have to do it in FR. I'm just trying to exemplify this. This the simplest algorithm that you can do for this. And the thing is, at each step I only have one multiplication because I only look at the left column, but we had four columns, so you have four equations to prove, so you have four multiplications mod q to prove in FR. So basically, per operation that you had to do, you have to pay four multiplications mod q. And at the end, then, so this is how you can prove the correct translation between the two tables. And then, of course, in FQ, you can then prove natively the operations there once you have done the translation. But the core part is really the translation. Once you have done the translation natively, you can prove it cheaply in FQ. So at the end, you have like some auxiliary proof on information. You have some auxiliary proof information like this. And if you want to check its validity, you check that this proof is correct. So which would attest that C0 is really the concatenation was in C1 and C2, assuming the length here to be correct. But the length is correct because the circuit checked it with the accumulator that we saw. And now you use the commitment C0 as, in what I showed before, as the commitment to each of the columns of AR. And there you can do the translation proof and then do the proof in FQ. So we're almost at the end already. So in terms of performance, so the metric I want to use to compare this, like to sort of assess the efficiency, is the gate count, the number of gates that this method entails compared to if you weren't using this method at all. So the gate that you're paying are the gates for this translation, especially with the mod q operations and the mod q multiplications that you have to do, plus the gate count in the proof that you're doing natively. And this is versus, if you were doing all the multiplications for all the operations in FR without using this method at all. So this is the performance metric. And in the paper, then there's a section where there are like different parameters for this. And basically, if you do some very stupid, MSM algorithm that you use, then you can already go up to a factor of 56. Of course, you don't want to do a stupid MSM algorithm. You want to do something by a factor of 56. I mean, the gate count is reduced by a factor of 50, 56. But if you um, do something more efficient, you're still not going to stay an order of magnitude more.
Yeah, but this is compared to non-native version, not
Yeah.
compared to cyclefold. And
Yes. No, no, no.
compared to cyclefold, it is like 2.5 or something like this.
Well, the cyclefold, looking at the paper, and I'm trying to discuss with Srinath at the moment to really get the numbers. The issue in cyclefold that I had personally, perhaps you have a better method for this, is that I didn't see really the parameters that were plugged in to obtain the numbers. So I couldn't really do an apple to apple comparison there. If then you can then check, okay, cyclefold, what does cyclefold claim compared to if you're doing non-native? There, cyclefold says you have like a 3,000, like that is the size of the circuit in the second group is like 3,000 gates only, but I'm not sure exactly again what the parameters are there that he's playing with. So, I just want to ask him that and try to figure out to have an
We
uh,
coded CycleFold with Nova, and I don't think you can make it 3,000 constraints. Like it's not extremely higher, but definitely higher than that for sure.
okay.
I think in the trade-offs for CycleFold, to be honest, are more in the decider side of things than elsewhere. Because in the decider, in like you basically need to, if you want to verify in the EVM, you need to verify one of the proofs non-natively in the main KCG proof that proves one of the sides of the cycle. And if you have CycleFold turned in, um, it turns out that the final decider is significantly bigger. So therefore, you need to
Yeah,
do
but
a lot
by
of stuff.
this metric, this method is just infeasible because it tries to commits to all your elliptic curve operations over a second group, and you get hit by actually a large circuit over a second group. So if you want EVM decider, then this method seems like even sort of worse, right?
So you're committing to I mean, the operations, you're not like, you're just writing down the execution trace, but then natively. So this
Yeah,
is,
yeah. I mean, the final decider will consist of still of two parts. First part is like your normal decider and this interface, which then moves your operations to the second curve, and then you do them all over the second curve. The
yeah,
point is that the circuit is large. It is like multiple elliptic curve operations depending on the amount of steps that you did. But in CycleFold, the size of the circuit is one operation. So if decider for CycleFold is already large, then for this thing it will be like much larger,
what do you
like
mean by,
proportionally.
sorry, what do you mean by one operation for cycle fold for the decider?
Well, in CycleFold, like your second circuit simulates a single operation. And basically what you are doing, you are folding a lot of these instances you're sort of doing the same thing, but not at the final step, but you're just sort of delegating these operations to singular instances of the cycle fold circuit and then folding them together. This, of course, has larger overhead, but in the end, what you are getting is already a folded instance of a circuit which is able to do a single elliptic curve operation. So the amount of stuff that gets popped out to the second curve is smaller
Okay, I see. So you're
for the
saying that
final decider.
only comparing the deciders is not a metric that is accurate enough,
Yeah, I
precisely.
mean, yeah.
It
Like,
bring
mhm.
the cycle fold pays more during the computation, but at the end is cheaper, and you're saying we're cheaper during the computation, but at the end we pay more. Basically, that's, I think that's
Yeah, but also you probably do not need to pay any of those because right now, like we have the GKRMSM research, and now you probably can just instead of committing to the second curve, you probably can just like avoid this commitment altogether and just run a non-native GKR.
at the very end. But then, are you sure that we would then be benefiting from all this? Because the whole point of this was precisely to do all the operations natively at the end, right? So I'm not entirely.
Yeah, but because they're already in GKR, it's almost basically our trick is very similar to what you're doing in a sense that you are sort of proving that you have copied the data between your original like transcript commitment and second commitment, right? But we do not have the second commitment, and we treat it sort of as a synthetic commitment scheme over a different field. So in a sense that you are asked to evaluate this polynomial in a point, and then we run this computation. But we do it for multivariate polynomials and not univariate, but the idea is very same, like very similar. So now we can just run GKR over this different field FR or FQ. I mean, the second field, your non-native field. And then you just do not get exposed to the commitments over the second curve ever.
Okay, I see.
That's the trick.
If you have a write-up, would love to see.
We have an implementation. We have better than write-up. We have an implementation. But yeah, we also have a write-up.
Okay. Yeah, I would love to see it. If you have one, please feel
Yeah,
free
okay.
to.
Yeah.
We can discuss that. I'm curious to know how it works in detail. Also, one thing is that at the end, usually whenever you have like your IVC proof refolding, at the end you don't want to actually reveal the witnesses. You actually computer snark that um, a witness for your folded instance at the very end. So you're doubling the cost of that when you're using cyclefold because you also have the second not doubling because the circuit is smaller, but you have to run also a second proof for the second curve cyclefold. So this cost also needs to be taken into account.
Yep. And I guess in line. Well, sorry, please finish first, Patrick, and we can maybe. Okay, okay. Thank you, thank you very much. Um, I have one question, um, which is mainly related to the decider, but in another sense. So, have you done any benchmarks that allow you to know basically when it's worth it to use all this machinery, like from which amount of elliptic curve operations delegated makes sense to use all this machinery versus, hey, I'm gonna just eat this up and that's it? Because at least with folding, it has happened to us a lot that it's never clear completely. Um, when it would make sense to go with a Stark, which almost free recursion, let's say, versus going folding, which can fold much faster than recursing, but at the same time you need to pay for the final decider. So do you have any numbers?
Unfortunately, I do not have numbers right now to tell.
Intuition?
Also, let me think. So I do know that for the size of the circuits that we're targeting, like 2 to 19, 2 to 20, like this definitely makes much more sense. The lower bound, I unfortunately don't have like numbers because it also depends like what's the size of the MSM you're going to do in circuit, for instance. Um, like for instance, let's say you have a function that you're executing that's doing some MSM size 64 or it's the MSM size of more, and this is fairly dynamic and moving. So there are like a lot of parameters to tweak because, like I said, we're not just doing like just one IVC, right? The context to which we want to use this actually, I mean, this is presented for building IVC, but like I said, stack proofs also fall into this, and this is where we really want to prove that you've correctly executed a function. And there, at each time, the function that you're executing does not really depend just on ASTEC on us. Um, so I don't really have like there are a lot of moving parts there. I don't really have a good idea, a good answer now as to that. I can try to ask more to have more benchmarks, and I can try to forward the numbers. But if I say anything right now, I don't think it's going to be remotely.
Sure, sure. No worries. Thank you anyways. Thank you. Are there any other questions from the rest of people? I would Okay, I will assume not. So I have one more if it's okay and you have the time. I don't know if that makes any difference or not, but is it more worth it to run like larger MSMs, like MSMs of a lot of points, or like a lot of MSMs but really small ones, like meaning a single elliptic curve operation, but do it a lot of times, or lots of elliptic curve multiplications combined in an MSM, but do it less times? Is it the same cost or changes?
It changes because like if you're doing, so it also depends. Okay, for this first one parameter, how you're going to split the binary representation of your scalars. That's the first thing. So assume if you want to use like an algorithm like Strauss algorithm or whatever, can go around, let's say you spin in chunks of 4 bits or something like this. And now, if you, depending on your MSM algorithm, you may actually minimize the number of steps compared to if you were just doing operations one by one. Because if I'm just doing one scalar multiplication then adding, this scalar multiplication, if I do double and add algorithm or some variant of that that's more efficient, then I pay a cost that's going to be proportional to the size of, like, to the number of chunks, basically. And I do this for each term in my MSM. So if you do one larger MSM, you're probably minimizing the number of steps that you're doing compared to the first approach. And if you're minimizing the number of steps, you're minimizing the number of group operations that you need to record, and then the number of group operations that you need to do at the very end. So I would rather go up than down in terms of the sizes. Then, but then, yeah, there's also, how large can you go given the other parameters, but definitely more.
Yeah,
Thank you.
I just wanted to add that n scalar operations can always be reduced to an MSM of size 2n using random linear combination. And if you use Pippinger, then pretty fast multiscalar multiplications becomes much more efficient.
Yeah.
So your answer is almost always.
That makes sense. Any other questions? Otherwise, I'll let you leave because I want to take more of your time. We've asked a bunch of stuff already.
No, all good.
I'll
Okay.
take it as a no. So again, thank you very much, Patrick and Tohru, for your time. I appreciate it a lot, you coming here and taking the time to go through the paper and explain like all the concepts and deep dive on it. Uh, yeah, mainly say thank you and hope to see you soon. And congratulations on your work.
Thank you for the invitation.
Thank you.
Bye-bye.
Cheers, everybody.
And Lev, please, I would like to see the write-up. Please don't forget if you
Sure.
go